All right, 12:31. I thought a few students are missing, but let's start. I think there are maybe 10, 20 slides residuals from lecture 3, so I'm going to try to cover them sort of fast. Just the concepts, there's nothing really substantial there. And hopefully in the majority of the lecture today, I want to go through some examples of parameterized conditional distributions, right? We said these directed graphs are defined with local conditional probability, so we need to see how we parameterize those. And then I'll give you one example, a little bit ahead of the schedule here, an example of how you compute the parameters on those conditional distributions given some data. The other part, I don't think we're going to be able to reach it today. It's basically an example, so either I will cover it on next Tuesday or I'll wait until maybe a month or two down the road. All right. So, reminder, we have seen 3 independent relations for directed graphs. Basically, the most powerful was this concept of deseparation based on this Bayes ball algorithm, or at least the Bayes ball sort of rules. In essence, this algorithm operates for both directed and undirected graphs. For directed graphs, we said we have to pay attention to these V structures, the explaining away. We have seen this directed local Markov property, ND, the non-descendants, this is the predecessors, and without really any rigorous proof, we basically said that these relations are equivalent to each other, right? So if you start with one, you can solve the rest, and all of them are actually equivalent to a factorization of the joint distribution over the graph that takes this form, okay? So if you remember, we did some examples where we started with a factorization like this, and then we proved this relation. You remember by doing marginalization and all of these things the lengthy way? The idea here now is, we're not going to start with this and then try to prove this. You know, if these are established from the graph, then this follows, and this is what we need. Okay? All right. So, just if you think that sort of you have 2 types of distributions or family of distributions. One, the family of distributions that factorizes this way over the graph, and then another family of distributions that satisfies all the independence relations defined by the graph. Then basically a theorem, which is more or less we highlighted, says that these 2 distribution families are the same. Okay? So the distributions that satisfy the independence relations, the conditional independence relations implied by the graph, or the distributions that factorize like this, they're basically, the 2 distributions are the same. Okay. Again, I am not going to be repeating things we have discussed. So let me bring some definition. I don't think we will make enormous use, but it is something you may come across in the literature. So this definition is of what is called the I-Equivalence, I standing from independence. So I of G for a given graph G is the set of all the conditional independent statements encoded by the graph. That's the definition. So for example, in the previous case, let's say if these were all the relations for this graph, then, you know, I of G are all these relations, okay? So it's the set of 4 conditional independent statements encoded by the graph. And 2 graphs, we call them I-equivalent if I of G1 is equal to I of G2. And you can show if G1 and G2 have the same undirected skeleton and the same set of V structures, they're I-equivalent. Okay, so they have the same independence relations. I'm only going to emphasize this thing that I marked here with red line, and it is very important for directed graphs, it says we can only identify graph structures up to I-Equivalence. So basically, if you try to identify, let's say, the directions of errors, is it to the left or to the right, you will not be able to do that. Okay? And in many ways, that's a limitation, basically, of the directed graphs, but then there are properties of directed graphs that undirected graphs don't have. But remember this, all right? You cannot identify the structure of a directed graph beyond this I-Equivalence, okay? And here's another important definition. Let's say we have a distribution P, okay? And let's define I of P to be the set of the conditional independent statements implied by the distribution P, right? No graphs or anything like that, just the distribution P satisfies certain conditional independent statements. We call those I of P. Now, for a given graph G, if the I of G is a subset of I of P, then we call I of G to be an I map of the distribution P. So in some sense, this is the buzzword here, we can use the graph G as a proxy for the distribution P. Now what you need to keep in mind here is that the distribution P may satisfy additional independence relations not implied by the graph, but every independence relation implied by the graph is satisfied by the distribution P. Okay? That's why the idea here is you can use it as a safe proxy for P. And actually I'm going to show you somewhere, I don't know where it is, a little picture from Bishop's book that effectively treats this G as a filter that allows through it only the distributions P that satisfy the independence relations implied by the graph. Okay? So if you have a distribution that doesn't satisfy the independence relations of the graph, so if this is not satisfied, then it cannot go through the graph. Effectively, you cannot use the graph to represent, factorize the distribution. So a trivial example. Let's take a discrete distribution defined, so x and y take values 0 and 1, and let's give some values of the joint probability P of x and y. I am not going to do the algebra. You can, it's all here, assuming the calculations are correct, right? But it comes up that you can show that P of x and y is equal to P of x, P of y. So the x and y are marginally independent, all right? So the I of P basically for this problem is the set that only involves x independent of y, right? No graph here or anything like that, right? So we have this distribution, and the only independence relation you can show is what you see here. So I of P is the set that only includes x independent of y. Now let's consider different graphs, and let's see what is I of G for each of these graphs. How many independence relations we have here on the left? There's no edges between x and y, nothing. So what is the relation between x and y? Independent. So I of G is the set that includes only x independent y. In this case, there is no independence relation 0, and there is no independence relation 0. So will you agree with me that all three graphs basically, they are can be used as surrogates for the distribution P? Remember, P has this property. All right? Now, can I use all of these three graphs to represent the distribution P? This, of course, because it satisfies the same independence relation, this doesn't require any independence relation, so any distribution will go through it. The distribution P will satisfy an additional independence relation, but that's okay, right? It will not violate anything in this graph because this graph has 0 independence relations embedded. Okay? The same in this case. So effectively, all three graphs, I1, I2, I3, etc., the I of G is subset of I of P, so they are I maps basically of the distribution P. All right? And this is sort of, if you like, a little graphical justification of what I said before, something that we put in red, here that says you can only identify graph structure up to I-Equivalence, all right? So here are all three surrogates, basically, three graphs, all right? And they're all, I-maps of the distribution P, okay? But those two graphs don't satisfy basically the underlying independent relations that P has, okay, which is this one. All right, this doesn't say anything. So, a theorem basically says if this is really formal language because already we have stated this 10 times. If G is an I map of P, then P factorized according to G. Okay? And factorized according to G basically implies this factorization that we have seen up to now. And the proof is sort of trivial because if you take the distribution P and you arrange the nodes in topological order using sort of the product rules of probability, you can write it as you see on the first line or as you see here. And then these previous nodes will be basically the parents and the non-descendants except the parents. So Z is the non-descendants minus the parents. And I can write this probability equal to that. Why? Because G is an I map of P. And there is the proof of the theorem. All right? So if G is an I map of P, okay, then P factorizes according to G. So basically the idea here is if P satisfies the independence relations implied by the graph, then P can factorize on the graph the way we have seen it, which is this, okay? So again, nothing extraordinary. We have seen this 10 times, but the proof is sort of, it only requires this property of conditional independence implied by the graph G, and this is what I have used, okay? Now, if you want to go the other way around, and I think it may be coming in a few slides, so I will not cover that, but if you want to start with a distribution that factorizes like that, and you want to prove independence relations such as this equal to that, you can actually do it directly by similar to the examples we did in the last few lectures, okay? So you can just start with that distribution, compute this, and then show that is equal to that. All right. This is just the example we discussed. We have seen this. No needs. Okay. Definition. Many definitions here. Nothing really amazing. So we defined a graph being an I map for a distribution. All right. So now we define a graph G to be a minimal I map, and a graph is a minimal I map when if the removal of even a single edge from the graph renders it not an I map of the distribution. In other ways, there is not a subset of G such that G prime is an I map of P. Okay? So that we call it a minimal I map. All right, and the last thing I want to define is the, so this is the graph I was telling you with, which is pictorially a nice way to think of this I maps, right? So the graph allows a distribution to pass through, all right, when the distribution satisfies the independence relations implied by the graph. But the distribution P can have additional independence relations not implied by the graph, right? But whatever is implied by the graph has to be satisfied by the distribution, otherwise this doesn't pass through. That's why, the concept here is you use this as a distribution filter. All right, so let me bring the last, rather complicated actually concept. We will do it with one very fundamental example. So if somebody gives you a distribution P of many variables, can you find a directed graph that has exactly the same independent relations, condition-independent relations, as the distribution P. You think, is that possible? So I can write down some weird distribution with some conditional independence relation. Can you find me a graph that is basically a perfect I map of that distribution? This is what I call a perfect map. I mean, can you appreciate that this sort of is a little bit more difficult problem than before, right? One is you make a graph and you say, okay, I know what relations are satisfied, so I know which distributions will satisfy that. Now, you're given a distribution P and you say, can you find me a graph that represents the distribution precisely? Okay, a perfect map. So the answer is, not every distribution has a perfect map. And a very fundamental example in the literature, you will find many pages devoted actually to this example, is an example with 4 variables. This is an undirected version of the graph that satisfies the following relations. A is independent of C given B and D, and B is independent of D given A and C. By the way, since the Bayes ball algorithm in principle becomes graph separation algorithm in undirected graphs, you may want to appreciate the fact here that B and D are independent given A and C, and A and C are independent given D and B, because in essence the path, let's say A and C are independent given D and B, because the path from A to C is blocked if you go this way, or is blocked if you go that way, with given D and B. Okay? So this graph separation is really this separation, the way we have seen it in directed graphs, but this undirected graph satisfies these relations. Okay? Basically, trust me that the Bayes ball algorithm basically doesn't care here about errors or anything. If you give D and B, then this path is blocked, then this path is blocked. Okay? If you're given A and C and you want to go to D, the 2 paths are also blocked. So these are the relations. And so you're asking is, can I find a directed graph that actually satisfies these 2 relations, this and this? And so here are 2 examples. This example satisfy these 2 relations. What do you think? I mean, you can, and I would suggest actually you spend maybe 10 minutes to prove if these 2 relations are satisfied by these graphs, but just look at it visually. Are these 2 graphs basically having the same independent relations as this undirected graph? So it says here, so let's say this graph, right? Where is B independent of D on this graph? What is the part of the Bayes algorithm that says that B is independent of D with no conditioning? Nothing is given right here, right? There is no evidence, so that's no condition. And to go from B to D, the only way is to go through there. And what is this? Is the V structure, right? This is the explaining away. These are parents, basically causes of the same effect A. So basically, since this is not given, B and D are blocked, so they are independent. Okay? So this relation has nothing to do with any of those 2, and similarly, B and 1 does not satisfy basically those 2 relations. So bottom line, not every distribution has a perfect map. Okay? So don't expect to basically have a distribution and then think of a graph that represents it. Usually you start with a graph with some mathematical intuition, and then you use that graph as a proxy for the distributions you want to work with. But the idea, if you do that, is you are limiting yourself to the distributions that satisfies the properties of that graph. Anything else, basically, you are not working with. It's sort of like a mathematical model, and you are have to obey the rules of that model, and if the model is wrong, you have problems. All right? Don't need those 2. Basically, they are repeating Okay, all right. So let's go to the new lecture today. The lecture has not been posted. Didn't have time. Didn't have time to have lunch or drink my coffee. So this is priority number 6. Okay? So it will be there by later today. So inference in graphs effectively means, right, that we are giving some evidence, and we have to estimate some unknown quantities, which can be either these hidden variables, and we will do lots of examples. Basically, hidden variables will be one for each data point, but also will be lots of static parameters, like the parameters in the conditional distributions that we need to estimate. So that's an inference problem, okay? For example, in hidden Markov models that we will spend maybe 2 lectures to go through the details, you estimate the hidden states if you're given, let's say, noisy observations, okay? For example, in disease-causing, in some medical applications, for example, you know some symptoms that the patient has, and you're asking, what is the disease that causes those symptoms? Okay? So it's basically the same thing as in HMM, but the variables, some of them can be continuous or discrete, so some mixing with space models may be the case. And there's many other examples as well. So the key equation that we discuss is basically this equation that you see here. And I'm going to do a very specific example today with discrete variables, hopefully before the end of the lecture, so you can see this equation in action. So here, the notation, this is the evidence. V means visible variables, A is the hidden. Theta are the static parameters, like the distributions defining the probability tables. You basically write the joint distribution like that, and this is the evidence. And the evidence basically requires marginalization over the hidden variables, as you see on the bottom. And these are the 3 examples basically that, or 2 of the examples that we mentioned. So this is the type of operations we need to do. And you notice here there is a big summation. So if these variables are hundreds of thousands, you need to do this in graphs in a very effective way, all right? Otherwise, this calculation would be computationally sort of not easy thing to do, okay? So don't get the impression, there is summation in XA, yes, but let's say X8 is 1,000 variables and each of them takes 10 values, then you're in trouble, okay? So in our sprinkler problem, the wet graph is the visible variables, right? So W is the visible variables. The hidden variables is, let's say in this particular case, we're interested to know if the sprinkler is on or off, okay? And cloudy and rain, they are really hidden variables, but I call them here nuisance variables in the sense that I only want to estimate if the sprinkler is on or off. I don't really care about the cloudy and rain. So they are hidden variables basically that I have no interest to do estimation. And if you have no interest to do estimation, you know what you need to do with them? You need to integrate them out, right? That's the Bayesian way, okay? So again, these C and R and S, they're really hidden variables, but in this case, I only care about the sprinkler. So this is what I'm going to call my query or hidden variables. These again are hidden variables that don't care, so I am going to integrate them out. And you can see the integration out on C and R. So when I write this, the joint probability of S and W divided by the probability of W, you notice in the denominator, since I have the joint of all the variables, I marginalize, this will be the probability of W, so I have to marginalize on S, C, and R. On the numerator, this is the joint of S and W, so I have to marginalize with respect to these nuisance variables, cloudy and rain, and this is what you see here. Okay? these marginalizations you can sort of think, visually, at least in the context of discrete variables, as some sort of collapsing big tables. So you can think here, if you have an XYZ table that is fully occupied with numbers, all right? So each of these little boxes, the cubes, contains the probability of X, Y, and Z having the particular values in this box, right? So if you want from this to get the marginal, effectively you can be collapsing in the direction of Z to get a two-dimensional table, right? So this looks easy process in 2 dimensions. If it is in 50 dimensions, really performing all these summations, it's an expensive task, okay? So keep that in mind. Again, for this particular problem, I give you, some of the calculations, and I think they were contained also in the previous slide. So effectively what you do is you plug in the joint distribution of all the variables, you plug in the values of S and W that you're of interest, and then you have to sum over all the possible values of this cloudy and rain. So these summations, each of these variables, let's say, takes 2 values, on or off. So you're going to have 4 terms that are as big as this. So 4 terms, and then here you're going to have 8 terms. All right. So generally, if the values of this table, if these tables are obviously represent discrete variables, that's a very easy problem, right? Very easy problem solved 30 years ago, so there's really no interest to do any research or write any papers because nobody cares, except in our class, right? Now, if these distributions are sort of Gaussian, I want to believe that everything has been done also 30, 40 years ago, okay? So there's no research to do. If these conditional distributions are members of the exponential family, I think the things already have been done and they don't look very much different from working with Gaussians. For those who don't know what's an exponential family of distributions, you may want to look on my slides from the course in the previous semester, and there's somewhere a nice table that tells you which distributions fit in that category and why things are nice when we work with them. But right now, I'm going to do 2 examples, basically with discrete variables and Gaussians, to convey the message basically on how to operate with these graphs. So let's start with discrete variables. If something doesn't make sense, stop me, because this sort of these examples were built on much more complicated graphs as we go along in the course. So let's say I have 2 discrete variables, x1 and x2, and they follow a multi-nully distribution, so they can take, each of them can take k different values. Each of these values with probability mu I, for the sum of all the mu I is equal to 1. So you can think, this is a generalization of a binary variable. I can take a value 0, 1. Here I can take k values, each of those values with probability mu1, mu2, mu k. Okay? So there are 2 cases. If the most general would be to write this joint distribution the way that you see here. Okay? For those not familiar with the notation here, these x's, all right, are 0 or 1. All right? So we said each of the values that these variables can take with probabilities mu I, all right, is 0 or 1, but we don't know which of the k variables is active. So what we do here, you notice is, this is the joint distribution. The probability of this take the value I and simultaneously x2 take the value j, we call it mu ij. All right? So this is the joint probability that this has the value I, this has the value j, and I put in the exponent x1i, x2j, and I take the product of all possible sizes and j's. Because in this product, only one I and one j from x1 and x2 will take the value 1, and everything else will be 0. All right? And something to 0 gives you what? Gives you 1. All right? So, because we don't know what the values of x's are, right? So if we want to write this, this is the only way we can do it. We're not going to write this and say, if x11 is equal to 1, this is equal to that. If x12 equal to that, then equal to that, because we run out of paper. Okay? This equation is compact. It works with a joint probability distribution mu ij, and it writes like that. Okay. So this is, it says the number of counts, the parameters in this problem is k squared minus 1. Where did this number come from? So we have k squared, and the 1 comes from where? So k and k squared, and the 1 comes from? What's the buzzword? Why 1? There's 1 there. Yep. Because when I sum, right, all the possible probabilities that, of the different states, the sum has to be equal to 1. It's part of the normalization. So k squared minus 1. All right. Now, if I assume that the distributions of x1 and x2 are independent, given the parameters mu, I can write, instead of writing this with disjoint probabilities mu ij, I can write this as the product of mu i's times the product of mu j's, okay? And here, the way it is written, I am assuming that mu is the same basically for both x1 and x2, okay? I don't see anything that separates the two, so right, they're independent. And actually, wait a second. I'm going to tell you in a second. Let's count to see what this number is, and then we will discuss what this is about. Where is the 2k minus 1 coming from? To describe each of these distributions, right, because this is the product of two independent distributions of x1 and x2, how many values, how many parameters I need for each of these individual product terms? I need k minus 1, right? I have k mu's, normalization of each of the p of x1, p of x2, so k minus 1, and then I have two of those. So the mu's here really are two different mu's the way I have it. The notation is not clear saying x1 has its own mu, x2 has its own mu. You see that? Yes? No? So basically this looks the same as this equation, right? So x1 can take k states. Each of these states I is with probability mu I. So let's say, for example, that this was a binary thing, right? So mu1 would be the probability that x1 is 0, mu2, which is 1 minus mu1, that the probability equal to 1. But here I have k of those states, so I write all of them like that. And because I have k states and k mu's, they have to sum to 1. So I really have k minus 1 parameters, okay? So I have two k minus 1 parameters. The implication is that these two mu's are different. Now, this is the key thing, right? So you notice here, for example, for this independent joint distribution, I have it like that. If you have a general distribution of m variables, basically the total number of parameters is k to the m minus 1, all right? This is similar to what we had here. So we have two variables, k squared minus 1. For m, it will be k to the m minus 1. So this is gross too fast for actually being able to do anything. Now, if the variables are independent, the number of parameters will be k minus 1 for each distribution times m, so very small number. And if I have a Markov chain, all right, where everything is defined in terms of these conditional distributions of xi given only the previous value, So this is a first order Markov chain. It says that the total number of parameters is k minus 1 plus m minus 1 k minus 1. Don't read and tell me what it says there. Where is this number coming from? So if I have a Markov chain, a first order, why the total number of parameters for m variables is k minus 1 plus m minus 1 k minus 1. K minus 1 is from, you remember to describe the joint distribution, you need to start with p of x1 and then p of x2 given x1 and then p of x3 given x2, etc. So p of x1 has k minus 1 variables, there it is, and then I have remaining m minus 1 variables, and they're defined through this conditional distribution. And how many variables I need for this? K here and k, I need k squared minus k, because this distribution for each value of xi minus 1 has to sum to 1. And I have k values of xi minus 1, so it would be k squared minus k. Okay? For a Markov chain, basically you can see the cost is linear in m. You can see here k to the power m. All right, that's not very good. So this is sort of the most trivial case, and the graph basically for that looks like this. All right. Now I know some of you have. I'm assuming you have taken other statistics courses. Some took the course last semester. Some have not. I know you got some homework problems where the assumption was that you look at the graph and you know everything from the skies, what it means. What I suggest is, if when you come across these things and you don't know, or you want to see more references, send me an email and I will send you very few pages of reading to see these things in detail, just in case you haven't seen it before. So this is the cases with discrete variables, and I give you a few examples. So let's look at the example on the top, okay? It says, we take everything to be discrete right now, okay? So I have a Markov chain, okay? x1, x2, xm. But x1 depends on, you can see here some parameters mu1, x2 on some mu2, xm on some um. And what does that mean? It depends. Means, look at this. You remember the general decomposition or factorization of the distribution over a directed graph, right? Looking at this graph, the distribution implied directly is the following: is p of mu1, all right? P of x1 given mu1, its parents, all right? And then the product of the distributions of x2 given x1 and given mu2, x3 given x2 given mu3, etc. So this product, okay? But also the product of p of mu2, p of mu3, p of mu_m. So this is the factorization over the graph, okay? So mu_m are basically the parameters that are needed to define this dynamical model that tells you how to go from xm minus 1 to xm, okay? And in this case, these variables, because they are discrete and take k values, this can take k values, and I'm going to need to put some prior, and a good prior to put is a Dirichlet distribution. Dirichlet distributions are going to come very often later in the course, so I really want you to look on Wikipedia and get some sense of what it's a conjugate prior basically to the multi-Nulli distribution, so it's very important to play, and it's also a very sort of interesting topic for research, because it has some very recent ideas are coming from Dirichlet processes, not distributions, okay? And especially for computer science students, this is a very important topic. Does this, looking at this graph, does it make any sense? All right? Again, the factorization these are all my unknown variables, my x's and my mu's, nothing, I don't give anything, right? So the joint distribution, I write it like that. Is this equation, like the first and second line, does it make sense? Very general. Right? So, again, you remember, you have to put these conditionals given the parents, but then some nodes don't have parents. mu1 has no parents, so it will come alone. mu2 has no parent, will come alone. mu_m has no parent, will come alone. All right? And because we would be interested to eventually sort of do Bayesian analysis on the parameters in the model, it's good to put a prior, all right? And that prior here is the Dirichlet prior that is going to have its own hyperparameters, alpha mu. Yep. From m equal to 2, thank you. Yep. Okay? So the product should be m equal to 2. I wish I can just say to my computer, please change. It doesn't. I don't know why the technology is not as sophisticated. So please remind me if I forget to change this. And the same, I suppose, there too, right? Okay. So this is the very general sort of setting, and I am taking the same problem, and I'm actually simplifying it enormously with a second probabilistic graphical model. So what's the simplification that you see on the second graph that is enormous? It's there. So what is the simplification? You can see it on the graph. So the parameters are tied. It means I'm using the same parameters to define all these conditional probability distributions. Okay? I mean, that's, of course, a major assumption, but you can appreciate doing inference with 1 mu versus doing inference with thousands of mu's. Okay? All right? So tying of the parameters makes things extremely easy. All right. I think maybe in passing we maybe advocated this problem, and we said it's not going to be used often in this course, but let me use this as a sort of a counter example. So let's say we have m variables again that they are discrete, and each of them can take k different states. And I'm interested in some sort of a classification problem. So I want, for example, to know if x1 to x, what's the probability of y equal to 1, right, given x1 and xm. So maybe y equal to 1 is 1 Gaussian from where my x data come, y equal to 0 some other Gaussian, okay? But I'm interested to just compute only to do classification this probability, okay? So somebody can build these complicated graphs that we had before and form the joint probability of y and all the x's, all right? And do inference in that graph. But an approach that is actually the best, if the only thing you care is this conditional probability, is actually to try to fit it in some nonlinearity, and that nonlinearity here is a sigmoid function. So basically what you say is, you know what, I'm going to model this as a sigmoid function, where I'm going to use some linear interpolation of the x's, okay, with some unknown parameters w. So no complicated graphical models, conditional distributions or anything like that. And the only unknown here are the w's, and I only have m plus 1 w's. All right? So if this is the only thing you care, all right, in the context of self-classification, these are the best ways to actually to model this using a parametrized, basically, model for this conditional distribution, rather than forming the whole joint distribution and working sort of in a generative sense. Okay, but this gives you only this probability. You cannot do much except just using that probability. So if that's good, you stop there. If it's not good, then you have to look at a more general way. All right, so let me, now I'm going to do the example that you guys Suvi gave in the homework. Okay? Anybody has worked on this problem? So let me work it for you because I haven't read the solution. So I don't know what if he's asking you. Maybe he's asking you to do what's on the slide, and if that is the case, you better correct my slide because I'm sure something must be wrong. All right, not just typed wrong, but so you guys find a mistake. So let's say so this is sort of a linear Gaussian model. You can think again of of a directed graphical model where these conditional distributions of xi given its parents, we're going to model it as a linear Gaussian model. What does that mean? Means we're going to take the mean of this conditional distribution to be a weighted average of the parents. This is what this is, plus some bias term, and then plus some noise. This is very generic, actually. This is what we call a linear Gaussian model. All right? So in this case, what is very particular to this linear Gaussian model is that the x's that you use to define the mean are defined from the parents. Right? These are the parents. These xj's are the parents of node I, but this mean is linear in xj. And then I plug in some noise v. So the unknowns basically in the problem are all these w's, right? The bias terms b's, and the variance is v, okay? So if you want to see this linear model written sort of in an algebraic form, you can say that xi is the mean value plus square root of vi times some normal Gaussian, okay, epsilon I, okay, with these elementary properties. So you can see this way, or you can see it this way. It is the same thing, okay? So linear Gaussian because you notice the mean is a linear function of the axis. The linearity comes everywhere. It's Gaussian because not only this conditional distribution of xi given the parents is Gaussian, but actually you can show, if you take all of these Gaussians, you multiply them with each other, if you expand and then you close the square, as they say, you can show that the joint distribution is also Gaussian. Right? It's a quadratic. I mean, and I am not doing the algebra because it's not worth it, but if you take the logs, right, and you come up, the product of all these distributions becomes summation of the logs, and then you get these squares, and if you expand them, you can basically get a square for to fit a multivariate Gaussian. So this leads to a multivariate Gaussian. So the problem here is we want for this graph that is represented by these conditional distributions, we want to compute the mean of all the nodes, and we want to compute the covariance, right? And I remember when the first time we got the homework, it says, oh, these are the equations. Well, I want you to prove them for me. They're my slides, but I want you to take some time to prove these equations because they're not obvious. Okay, nothing is obvious in life. So if you take the mean, here this is the mean of the conditional distribution of x given its parents. Okay, so if you take the mean of xi is actually let me use this equation. The mean of xi is summation over the parents of wij, the mean of xj, plus bi, and the mean of this, which is 0. All right? So effectively, using this little equation, this means if you put them together, all right, if you calculate them recursively and you put them in an order, it will give you the mean of the multivariate variable x. Everybody sees this equation? I'm just using this, and I take the mean of xi, the summation, then it will be the mean of xj. This is constant. The mean of this is 0. All right? So basically I have a recursive relation, and those means, when I put them together in a vector form, will give me the mean of vector x. Okay? Nothing fancy. Now, the mean of the covariance is a little bit more complicated. The mean of the covariance is given sort of a similar expression. This coefficients wjk, where k are the parents. I have to use a k here because there's an I and a j there, right? So wjk, the covariance of xi with xk, covariance of xi and xk. So notice here there is a j. From there is a k that are the parents of j. And then there is an extra term that is a delta function, right? So equal to 1 if I and j is equal. Otherwise, 0 square root of vi vj. These are variances, right? So I need to have vi vj. And when I write this equation, I forgot to maybe to put this on the previous slide. This is for I less or equal to j. So you may want to take a note. So this, in the way that I have it, is for I less or equal to j. Okay? If you know this, right, you can, if you need something else, you can use symmetry and you can get for I greater than j a similar expression, but this is for I less or equal to j. Okay, how do you prove this equation? All right, the homework I know doesn't ask you this, or I don't know if it does. Does it? Does it say anything? Does it say prove it? Okay. All right, so if you want to prove it, so if you want the covariance of xi and xj, by definition is this. So I keep xi minus the mean of xi, xj minus the mean of xj. I'm using basically this relation, this linear starting point that I had there, and I'm subtracting the means of xi and xj, and basically I substitute this, and it will take this form, where k is a parent of j. Okay? So now I'm going to have a summation of the parents of j, wjk, and then I'm going to have the expectation of this parenthesis times that is the covariance of xi xk. So the first term is the easy term, and then there is the expectation of this parenthesis times this term that involves epsilon j, all right? And if the previous equation is correct, that product of expectation needs to come to be equal to this. And the only way that I have been able to actually prove this is sort of doing it recursively. Okay, so if you guys come up with a cleaner way, not only you send me the right proof, but you send me the correct equation to cut and paste on my slides, okay? Because I'm not particularly happy with this derivation, but so again, we want to prove the expectation of this times that is equal to that, and the way that I do it is I write this from our original equation, right? I substitute this in terms of its parent values, right? This is the expectation, okay? And then what I started doing is, you remember I have a node I here, the parents are before node I, and the parents of I are before that. So what I do is I recursively introduce the parents of I, and then for each parent of IM, I introduce its parents n, and I keep doing this until I reach node 1. All right? So when you do it sort of this way, okay, it comes up that when you take this times that and expectations, the contributions you will get from this summation drops to, to 0, and then you're going to have basically this Vj, Vi, epsilon I, epsilon j expectation, which effectively, at the end of the day, will give you this. I'm highlighting the proof as part of your homework. If you want to look at it, okay, it's algebra, all right? But bottom line, this is how you compute expectations. This is how you compute the covariance. Both equations are recursive because to compute the covariance of xi, xj with I less or equal to j, You need the covariance of xi with the parents of j. And to compute this, you need the parents of k, and et cetera, until you reach the root node. So let me give you an example. If you have 3 nodes, so let's look at this, the first equation, the expectation. Can you tell me where this equation comes from? All right, I remind you this nice equation. The expectation of any node is wij times the expectation of the parents of j. Okay? I'm sorry, the parents of I times plus bi. So if I look, let's look at node 3. Okay, node 3. So node 3, I want somebody with genius memory to remember this equation, right? Node 3. What are the parents of node 3? 2. Just 2. So I'm going to have W3, 2, the expectation of x2, W3, 2 times the expectation of node x2. And what is the expectation of node 2? The expectation of node 2 will be W2, 1 times the expectation of x1. And what is the expectation of x1? Is b1, because there are no parents. All right? So when you put all of this together, you get this nice expression of this and this. And similarly, do check, for example, let's say the covariance of x1 and x3. I have the formula here, so we don't have to go back and forth. This is the formula that says k are the parents of 3. The parents of 3 is 2. So it will be W3, 2 times the covariance of x1 and x2. The covariance of x1 and x2, you need the parents of 2, which is 1. So it will be W2, 1 times the covariance of x1, x1, plus this delta function 1, 2 times v2. This function is 0. So you get W3, 2, W2, 1. And the covariance of x1, x1 is v1. Okay? So it's sort of a complicated, painful calculation, but on the other hand, it's a closed form solution. You have the mean. Just by playing together with this conditional probability distributions, you can compute the mean of the joint distribution and the covariance, and you have everything. All right? Now, how many parameters on this model? So again, don't read everything. The parameters in the model are these variances, and there are d of those because, I suppose my graph has d nodes in this case, right? So I have d variances, and then it says the parameters wij are d squared minus d over 2. Where do I get that? You remember this W is defined your dependence on the parents, right? So if I'm interested, let's say, on W12, how much is W12? There's no W12, 0, right? I mean, the only thing I have here is, let's say if I look at node 3, I have W32 and W32 is non-zero because the parent of 2 is the parent of 3, all right? So here what really I'm looking is this W to be a lower triangular matrix, and a lower triangular matrix in d dimensions is what? Totally d squared minus d in the diagonal, then you take half, you get d squared minus d over 2. So it comes that this complicated linear-Gaussian model, if you sum these two, is d times d plus 1 over 2, which is actually the same as the covariance matrix of a Gaussian, all right, a symmetric covariance matrix. So don't be surprised that that's the case, right? Because we proved that effectively the joint distribution is a Gaussian, all right? So obviously this problem needs to be sort of equivalent to to this order of parameters required for a multivariate Gaussian, basically, to define the covariance matrix. Okay. Now I'm going to give you another sort of approach to this problem that is from Murphy's book, and it is sort of a way simpler calculation without any recursive relations. Okay, so you may appreciate this derivation because it's only one slide or two. So I kept the notation from Murphy so I don't mess up any equations. But basically I'm looking exactly on the same problem, right? So instead of V, this conditional variance here, he is using sigma t squared. This is my bias term was B before, so it's mu t. It's exactly the same problem, okay? So what he does is the following. He basically, you remember our original equation that I had before, right? X t equal mu t plus, what have I done here? Actually, the only thing I have done is I subtracted the mean from the values of each node, okay? So, from this node and the parents, basically what I have done is I subtracted the means, okay? And so this is the similar equation with what I had before. This is like my noise level epsilon that I had before, but by writing the equation like that where the means of these nodal values come explicitly, I can write this whole equation as a vector form as follows. X minus mu as a vector equal a lower diagonal matrix W, similar to what we had before, times X minus mu. Okay? And I can write this as the matrix S, and in this case would be the diagonal that contains the noise variances. Okay? I suppose, yes, this before we had the square root of the variance, so this is, it's the standard deviation, so this is correct. So S is the diagonal of sigma times the vector Z. This is the same equation I had before. The only difference is now, right, that I can write this as a matrix equation where what is different from the expression we used before is that instead of x's, we have x minus the means of the nodal values. And there is a reason to do this because, so this is our equation. If you define, just to start with, E to be S times Z, where S is this diagonal of the standard deviations in the conditional distribution. So this is E. X minus mu, you can see from here, times I minus W is going to come to be E. All right, so if I write this explicitly, E equal I minus W, all right, a nice invertible matrix, times X minus mu, all right, and effectively I can solve for X minus mu by inverting this matrix I minus W times E, all right, and okay, so E is S times Z, all right, so let me call this matrix U, all right, call this matrix U times S times Z, all right, so X minus mu is U times S times Z, all right, and why is that important? Look at this, and this finishes the whole derivation. If you're interested to find the covariance, where we did the complicated calculation, the covariance of X the same as the covariance of X minus mu. X minus mu from this equation is U. This is U, by the way, the inverse of I minus W's of the weights, all right? So the covariance of U times S, S, you remember, is the diagonal of the conditional standard deviations. S times Z, Z is my noise vector. And the covariance of U times S times Z from classical identity from your probability course is US times the covariance of Z times the transpose of this, SU transpose. So this is identity, so you get US squared U transpose. So to find the covariance of the joint vector x, what you need is you need to compute u, and u is in terms of the weights, and you need s, and s are the noise variables, the noise standard deviations of the conditional distributions. So no recursive calculations at all. The recursiveness has disappeared with one trick, and that trick is to work not with the x variables, but with the x minus mu variables. Okay? So, so if you want really to implement this linear Gaussian model, this is sort of the easiest way. You can get basically the expectations the way we did in the earlier slides. The expectations are very easy to do, but to get the covariance, basically you do this calculation, compute u, and then us squared u transpose will give you the covariance in one step. Okay, 136. I was told that Subik told you about the plate notation, all right, or something like that? No? Yes? All right. So what's the idea of the plate notation? It is sort of handy when you collect data and you don't want, to have a graph that is sort of expands forever. You want something that is really compact. So let's look, for example, at this trivial case where you collect data x1 to xn, and they all come from some distribution, some unknown parameter theta. A good way to represent this, so here actually I should have dots, right? It's x2 here, x3, etc., xn. So a good way to represent in a compact fashion this is to represent this with a plate notation that goes as follows. You form a box around xi, and you indicate that you have n instances of xi, right? You have n different realizations of xi, and all of these realizations have the same theta, or they come from the same distribution that has the parameter theta, so theta has to be outside the box, because only things inside the box repeat. Things outside the box are basically independent of I, okay? So this is basically equivalent to the notation that you see here. For simple problems, you can do this. For more complicated problems, this may be handy, but you have to do it carefully because some of these boxes in complicated distributions may be nested, and you can sort of come up with the wrong the wrong conclusions because your distribution represented by this graph or this graph is not the same. So in this case, if you are interested in the joint distribution of all the variables theta and xi, basically what you're going to have is you have the probability of theta given its parents, no parents, so p of theta, and then you have n instances of the probability of xi given theta, which you see with this product here. So this is the joint distribution, and it's really identical to the joint distribution that you see there. Okay? So this again, it's a more compact way, and it's called the plate notation for representing graphical models. All right. So if this data xn comes from a Gaussian that has some unknown mean and variance, let's say standard deviation sigma, this is the plate notation for representing some IID data from this Gaussian with parameters mu and sigma. All right, so the joint distribution is P of mu, P of sigma, and then you have n instantiations of the probability of x given mu and sigma. All right, these are its parents. So this is one option. You want this option where you have all of this, everything indicating that every node x depends on mu and sigma, or if you prefer this. This is clean. Right? It's a much more clean notation. Okay? All right. So let me finish. We have exactly 5 minutes. Again, for those who have not seen regression models, I will suggest that you look on my lecture in the fall. and for the exact same problem, basically notation. I don't think we're going to come back to regression problems in this course, but right now I just want to give you a graphical model representation for regression, for Bayesian regression, to see how it works like. So let's say we are given some data, x and t are the target values, and we try to do Bayesian fitting in the sense that for some new x, we want to be able to predict the value of t and also the uncertainty in t. So what we do is we come up with a regression function that is basically, in this case, a linear model. Okay, so wi times xi. Okay, and these coefficients w, we take them as random variables, so we're going to put some prior on them. All right, and so the joint probability of t and w is, you can think here of t being our measurements at some given points x, but in this equation is not shown. But the joint distribution of what I have observed, which is t, and of this unknown parameters w, is the prior w times the likelihood of each data point tn with known parameters. So this is how the regression model looks in the standard sense. All right, these are the observations t. The parameters w are unknown. All right, so for every given x that the graph doesn't show, and I emphasize this, I need to know what w is. So t1 depends on w, t2 depends on w. So this is the graphical representation. In a plate form, it becomes trivial. And to make it interesting, and this is the type of regression problem we did last fall, if you're going to put a prior on w that has hyperparameters on it, and we call those hyperparameters alpha, and if you also want to make these values of tn to be noisy with some unknown noise sigma square, then this is the very general description of a Bayesian regression model. Okay? I know there is a lot there that you may need to study, all right? But the idea here is for every xn, all right, I measure tn, and my actual, function varies basically from tn by some noise sigma squared that I don't know what it is. Okay. In my regression model, I need these coefficients w. All right, that define my regression function, and the w is the same regardless of n, little n. And because I put a prior on w that has some hyperparameters alpha, I need to basically have an error from alpha to w. So this plate model represents the joint distribution that looks like this. Okay? Again, there is way too much there, right? So this is the joint distribution of things I observed, which is this noisy function evaluations and the parameters, given the inputs x, now the inputs come here, given this hyperparameters alpha, and given the noise sigma square I don't know. And the joint distribution, you can read it from the graph, but for those who have never seen these graphs before and they know about regression, basically what it is the prior. This joint distribution is the prior. This is, you can think of this actually, the joint distribution, as the unnormalized posterior. All right? Okay? So it is the prior that depends on alpha. All right? That's that part of the graph. And then you have the likelihood model that gives you the probability of Tn given xn, but that probability depends on the noise sigma squared and depends on w. So effectively, you don't have to write this lengthy equation. If I look at this graph, I know what is going on and I know what the problem is. And that's why when you got a homework problem, Suvik said they know everything, so let me give them a plot. They will figure out what it means. Says, oh, here's an equation, here's a plot. Go and write a program to do this. Okay? So that program basically would need to require that you understand that this graph implies all of this. Okay? Now, in this graph, there is nothing for predictions. Basically, it has only the information, the values for training, the t values and the x values, the priors and w, but there's nothing for prediction. So if you want to add things for prediction, so if you want, let's say, not only to train the model, but also to be able for a new x to predict what the value of the function is, t hat, this is the whole diagram that includes the joint probability distribution of everything. So the distribution of w, the t data that you gave, but also the prediction t that you want to do at the point x. And you notice it contains the anormalized posterior, which is the prior times the likelihood. All right, this comes again from what we did before, but also now it has, so this is sort of the, the posterior of w, literally, times the likelihood, okay? And the likelihood for the prediction point is, if I knew w and sigma squared for my